All right, let's then move on to some of the questions that I have as review questions. Here is one. It says the work done on a charged particle by the magnetic field can be positive or negative, must be negative, must be positive, must be zero, none of the above. All right, take a minute, talk to the person next to you, think about the question. All right, the correct answer here is zero. The work done by the magnetic field on the charged particle is always zero. Can anybody think about why that would be the case? What is the definition of work? Go ahead, please.
Force, like,
Yep.
cross with displacement.
Yeah, force dotted with displacement is the. So what is that? So here, so one way to think about it is we are trying to figure out what is the work done by the magnetic field, and that should be the dot product of the magnetic field with, sorry, the magnetic force with the displacement, right? What is the magnetic force? Remember, magnetic force on a charged particle is Q V cross B, right? Where B is some external magnetic field, V is the velocity of the charged particle, and Q is the charge, right? Now, which way is the direction, is the displacement? Is the direction of displacement always in the direction of the velocity? It is. So displacement, the displacement and the instantaneous velocity always point in the same direction. On the other hand, look at this. Force is a cross product of velocity and magnetic field. So force is always perpendicular, right? This is a symbol for perpendicular to the velocity vector. And this means that force is always perpendicular to the displacement vector, right? And if those are perpendicular, you can see that this thing will be magnitude of the force times magnitude of the displacement times cosine of the angle between the two. But we are saying that this angle theta between the force, magnetic force, and the displacement vector will always be 90, right? So the thing is, what we are saying is that this will be f sub b d times cosine of 90 always. Why? Because we know that the force, magnetic force and velocity, or magnetic force and displacement, are always perpendicular, and cosine 90 is 0. And so the work done is 0. By the way, could we have also figured it out using work energy theorem? Do you remember work energy theorem? It says that work done by the net force is change in kinetic energy. Does the kinetic energy of the charged particle change due to the magnetic force? No. All that magnetic force does is changes the direction of velocity. It does not change the magnitude of velocity. The charged particle will never move faster or slower due to the magnetic force. So if you remember, using the work energy theorem, let me write it over here. So another way, alternative way to reason is to use your work energy theorem, which says work done by the net force is equal to kinetic energy final minus kinetic energy initial. But in this case, so we know that kinetic energy final should be equal to kinetic energy initial, because all of this is half times m times v square, right? Why? Because the speed does not change. By the magnetic force. Only direction of velocity changes. So only the direction of the velocity vector changes. And remember, kinetic energy is a scalar quantity, half mv square. So if this is equal to this, we know work done must be 0, right? So this is really, half mv square minus half mv square, which is really 0. So the work done is 0. So there's no work done by the magnetic field. Magnetic force never does work on a charged particle, period. It just makes the particle move in a circle at a constant speed, right? All right, sorry. Let's look at another question here. Okay, this question says, wire 1 has a large current I flowing out of the page as shown in the diagram. So this one has a current flowing out towards you. Notice this dot here. And wire 2 has a current going into the board. The question is, what is the direction of magnetic field at point P here, which is a little bit closer to this wire than to this wire, all right? And you have been given all these choices. You have 1 minute to answer this. Please talk to a person next to you. All right, the correct answer is A. Up is the correct answer. And it's great. Most of you, it seems like, got the correct answer. And you can see the correct answer is A because the magnetic field due to both wires point up at that point. How do you know? You can use right-hand rule too. Remember, I taught you 2 different right-hand rules. One is the right-hand rule for cross products, which is also called right-hand screw rule. And that's what you would use for cross products like this, B cross B or L cross B. Those things you use one kind of right-hand rule which says put all of the fingers in the direction of the first vector, curl it in the direction of the second vector, your thumb will point in the direction of force, for example, the third vector, the cross product vector. That is one right-hand rule. This is a totally different right-hand rule which is about magnetic field. The right-hand rule for magnetic field is the right-hand thumb rule, which says put your thumb in the direction of current and your fingers will curl around in the direction of magnetic field. Remember, we said long straight current carrying wire will have its magnetic field which will form circles around it, concentric circles with wire at the center. So in this case, for this, due to this wire, you can see if you put your thumb in the direction of current which is coming at you, you can see that the magnetic field lines are forming closed circles like this. So they are going in the counterclockwise direction, right? So then, and the direction of magnetic field at any point on that circle is going to be tangent to the circle. So then if we want to know what is the direction of magnetic field here, let's draw a tangent, and since it's in the counterclockwise direction, you can see the tangent is pointing up, not down, right? Similarly, let's try to do it due to this cross thing. Again, I'll put my thumb in the direction of current, which is going in for this thing, and you can see my fingers curl around in the clockwise direction this time. So the magnetic field due to this cross thing is in the clockwise direction and it's forming circles. So if you think about a huge circle which passes through this point P, again you can see since it's clockwise, the magnetic field at point P will be tangent to the circle which is pointing up. So the magnetic field due to both of these wires is pointing up, and so the net is up. Does that make sense? Any questions, folks? All right. Let's move on and let's try this one. It says 2 long parallel straight wires carry equal currents in opposite directions. The force that each wire exerts on the other one is 0, mutually attractive, mutually repulsive, parallel to the length of the wires, and none of the above. Take 1 minute. This is something that I am going to discuss more today, but you might be able to figure it out by thinking about all the things we have already learned.
That's just the magnetism. Oh wait, no, but there was four cells there. We were doing that one thing. But it would cause us to see what's
All right, it turns out that the correct answer is mutually repulsive. Boy, it looks like many of you got it right. So the thing is, the answer is C. Okay, so let's try to figure out, the first thing we'll do today is we'll really see, based upon everything that we have done, why the thing should be repulsive. Does anybody want to say why it should be repulsive? Can you reason through it using these things? You know this, right? You know F of B is equal to I L cross B. Right? You know this. And you also know how to find the magnetic field produced by a current carrying wire. Can you try to reason with these two things? Anybody wants to make a reasoning, or do you want me to go over it? Okay, so let me just go over the reasoning for this. And it's very interesting because this is not what you would expect. If you are thinking that two wires carrying current in the same direction somehow, should not like each other, that's not the case. They actually like each other. And let me first show you the demonstration before we go over the reasoning for it. So here is these are two different cases. First, let's see when the wires are carrying current in opposite directions. So see, this arrow shows this wire is carrying current up. This arrow shows the wire is carrying current down. Right now the current is 0. If there's no current, the wire doesn't behave magnetic, right? The wire starts behaving magnetic and has a magnetic field around it only when there's a current flowing through it, right? So let me try to turn on this switch and you'll see wires. What do you expect there? Wires repelling each other, right? So this one is feeling a force in this direction due to that wire, the current in that wire, and this one will feel a force due to this wire in the other direction. From Newton's third law, these forces must be equal in magnitude and opposite in direction, right? Let's try. Watch. I cannot pass the current for a long time because Jim is going to really be upset. I'm going to, burn the wire. So watch. Do you see? I have to stop this because the wire will start melting. The current is so high that the wires start to melt because of the I square times R, power dissipation in the form of heat in the resistance of the wire. So watch one more time. Do you see the repel? So this one is feeling a force due to that current in this way, this direction, and this one is feeling in that direction. I mean, if you know the force on one of the wires, the force on the other wire is easy to predict using Newton's third law, right? That you learned in physics 1. If one of them is east, the other one must be west. Okay, on the other hand, if the wires are carrying current in the same direction, like here, right now there is no current, so there's no force. But as soon as I pass current through it, what do you think will happen when the currents are in the same direction? They should attract. Let's try. So this one will feel a force that way, and this one will feel a force this way. So the two wires will touch each other. Watch. Do you see? Oops. So you can see that the wires actually attract each other when they have currents in the same direction. They repel when the currents are in different directions. Let's try to understand why this is the case. Okay, so let's first talk about what? Do you want to talk about currents in different directions? Let's talk about it. Case in current in opposite direction. And I'm talking about long straight current carrying wire. These wires are long and straight. Here is the thing. I want one of you to tell me, oh, we said they are carrying current in opposite direction. So let's say that this is a wire which is carrying current down, and this is a wire that is carrying current up. Let's call this current I1. Let's call this current I2. So this is wire 1, this is wire 2. Does anybody remember from the last lecture what is the magnitude of magnetic field produced by a current carrying wire at a distance r away? Remember we used Ampere's law? Do you remember that? Yeah? So using Ampere's law, what do you think, do you remember what we found for what is the magnetic field produced by a current carrying wire? So if you recall from Ampere's law, and what was Ampere's law? Ampere's law was this: integral over any closed loop of B dot dl is equal to mu 0, a constant, times the current that is enclosed in the loop. I enclosed is the current enclosed. Using this, what did we say was the magnetic field produced by this current, let's say I1, at a distance r away? What is the magnitude? Let's just worry about the magnitude, because the direction we can use the right hand thumb rule, right? Using the right hand thumb rule, we already know magnetic field lines form closed circles, and in this case at this point the magnetic field will be going into the board, right? On this side of the wire the magnetic field will be coming out, on that side of the wire everywhere the magnetic field is going in. I want to know what is the magnitude. How did we do it last time? Anybody? Because this has already been done last time. Tell me how I would use Ampere's law. To use Ampere's law, I have to choose an Amperian loop. What would be a good loop to choose? Will it be a circle? Yes, I should choose a circle with this wire at the center, and that point where I want to find the magnetic field magnitude as a point on the circle. In this case, can you guarantee from the symmetry of the situation that the magnitude of magnetic field should be the same everywhere? It should be, right? Then I can pull the magnetic field out, the magnitude of magnetic field out. Also notice that dl and magnetic field point in the same direction. So dl is along the tangent, it's the length vector, infinitesimal length vector, and magnetic field is also forming these closed loops, which are circles anyway. So the angle between b and dl is 0. So what we said last time is that integral b dl cosine theta, the angle between the two, is 0 degrees. This is mu 0 times I enclosed. Cosine 0 is 1. B is constant over this loop, so B gets pulled out. And so all I have is integral dl is equal to mu 0 times I enclosed. And this says, what is integral dl? Is that the perimeter of this whole thing? It is. And that's just 2 pi r, right? So what we get is that B times 2 pi r is equal to mu 0 times the current enclosed, and the whole current is enclosed, right? So if this current is I1, that whole current is enclosed, and so what I get is that B magnitude is mu 0 I1 over 2 pi r. I'm not doing anything new. This is something that we already did last time. It's all there in your notes, you know. But the point is, if I ask you what is the magnetic field, suppose this distance was d, and suppose I ask you what is the magnitude of magnetic field produced by wire 1 at the location of wire 2, what would you tell me? You know, because the question is, why are these wires attracting or repelling each other when there is a current passing through them? They are attracting each other or repelling each other because each wire is producing a magnetic field, right? If I'm producing a magnetic field and you are producing a magnetic field, shouldn't the two magnetic fields interact with each other, right? So the thing is, because of the fact that I'm producing a magnetic field and you are, and there is a wire in my magnetic field, in the magnetic field that I have produced, that wire will feel a force due to that magnetic field. Similarly, that wire is producing a magnetic field at my location and I am a current carrying wire, so I will feel a force due to that magnetic field because that magnetic field is acting like an external magnetic field for me. Is everybody understanding? Because each wire is producing a magnetic field at the location of the other wire, and that magnetic field is acting as an external magnetic field for the other wire, and hence that wire feels a force. Because we have learned this, we have learned that the force on a current carrying wire, the magnetic force on a current carrying wire is I L cross B. So if I am a wire, if this is me, and this wire is producing a magnetic field here, that magnetic field produced by that wire is an external magnetic field for me, and I will feel a force due to that. Similarly, I am producing a magnetic field at the location over there, and so this wire which is carrying current will feel a force due to me, which will be given by this. So in order to find the magnitude of this force and the direction of the force, direction you already saw that the wires are repelling each other or attracting each other depending upon whether the currents are flowing in the opposite direction or in the same direction. We will have to make use of both of these things. Okay, so let's go slowly because this B is this B here. Because this is the magnetic field produced by, say, this wire at the location of this wire or this wire at the location of this wire, right? Of course, for this one, I'll have to put I2. So let's go slowly. Who wants to tell me what would be the direction of magnetic field? Let's first talk about direction, which will be given by your right hand thumb rule or the rule for the magnetic field. What would be the direction of magnetic field produced by wire 1 at the location of wire 2? Go ahead, please. Into the board, very good. So she's absolutely right. This will be the B external produced by wire 1. And let me give it a name instead of B external, let me call it B1. So that you remember that this B1 is the magnetic field produced by wire 1 at the location of wire 2, because wire 1 is producing magnetic field around it, which are circles. And is everybody seeing this is into the board? Okay, what I am interested in right now is what is the force F2? That means what is the magnetic force on wire 2 due to wire 1, due to current in wire 1. Okay, so I know already from what we have already learned is that F2 should be equal to the current in wire 2, I2, times the length of wire 2, let's say length is L, cross B external. Right? Let's say that this length is L. These lengths are L for each of these wires. Is everybody with me? That this would be the force on wire 2, whatever is the current in it, times L cross B external. But B external is really a field, magnetic field that is produced by wire 1. So I can call this B external B1. Right? Is everybody with me at this point? Okay, let's worry about the direction of this force. I'm not going to tell you. Everybody should use their right hand rule for force. This is the right hand rule for cross products to tell me which way is their, which way does their thumb point if they use this rule L cross B1. L is in the direction of current. B1, already, somebody told me that it's cross product. She told me it's a cross. That means it's going into the board. Who wants to tell me how to figure out what is the direction of force there? Did you want to say? Go ahead. To the right? Yeah, how did you do it? It is to the right. So basically what you find is F2 is to the right. How do I do it? I will do L cross B1. L means put all of your fingers in the direction of the first vector L, which is in the direction of current pointing down, right? Cross it in the direction of B1, which is the magnetic field which is going into the page. You see my thumb points that way. So that already shows that this wire is being repelled, just like what you saw here. You saw that this wire was repelled. And that's exactly what we are seeing. Let's now try to figure out what is the magnitude of this force. What will be the magnitude of this force? The magnitude of the force will be I2, the magnitude of length, times the magnitude of B1, times cross product means sine, theta. Sine is the sine of the angle between L and B1. What is the angle between L and B1? Look, B1 is pointing into the board, right? L is in the plane of the board. The two things are right, perpendicular to each other. So this is just sine 90, which is 1. Sine 90 is 1. So basically what we find then, what we find is that the magnitude F2 will be equal to I2 times L times B1 magnitude. What is the magnitude of B1? Somebody from that side, what is the magnitude of B1? B1 is the magnetic field that is produced by wire 1 at the location of wire 2. So what is B1? Anybody folks, what is B1? Go ahead please.
mu naught I over 2 pi r.
Yeah, I already wrote, actually this is B1 because this is mu 0 I1 divided by 2 pi r. The R here is D, right? B1 is the magnetic field produced by this wire which is carrying current I1 at the location of wire 2. So in this case we can see that B1 will be mu 0 times I1 divided by 2 pi times the distance between the two wires, because we are really talking about how much is the magnitude of magnetic field produced here from the wire that is producing the magnetic field. Is this making sense? Okay, so if that's the case, let's try to plug this here. Then the force will be I2 times the magnitude of length times B1, which is mu 0 I1 divided by 2 pi d. And so you can see that F2 is mu 0 times I1 times I2 divided by 2 pi d times L. If you wanted to find the force per unit length, that will be mu 0 I1 I2 divided by 2 pi d. This is the magnitude of force. By the way, if I asked you this question, will the magnitude of force per unit length on wire 1 due to the wire 2 be the same as this? What would you say? From Newton's third law, shouldn't it be the same? Do we even need to redo a calculation? Okay, if you don't trust me, a lot of people just didn't shake their heads, so let's just work through the whole thing, because let's just see that Newton's third law is not violated in this case. So basically what I'm trying to say, this is the force on wire 2 due to wire 1. First of all, you notice it depends upon the product of the two currents, and it's inversely related to the distance between the two wires. Now I want to do the opposite, which is, how many people believe that Newton's third law works here? Okay, it looks like a lot of people do, but let's just verify it for the sake of verification. So we want to see that the force F1 over L is exactly this, mu 0 I1 I2 over 2 pi d. All right. So in order to do that, what should we do? So this is my wire 1. This is my wire 2. Now I want to know what is the force on wire 1 due to wire 2. Can I write it like this? F1 should be equal to I1 L cross B2. Can I write it like this? This is the force on wire 1 due to the magnetic field produced by wire 2 at the location of wire 1. Right? I want somebody from the third row to tell me what is the direction of magnetic field produced by wire 2 at the location of wire 1. Tell me. Into the board? Okay. The way, yes, that's absolutely correct. How do I do it? Put my thumb, use the right hand rule for the magnetic field, right? This is the thumb rule. Put your thumb in the direction of current. Do you see that the magnetic field lines are forming closed loops? Like that, in a way that magnetic field on that side of the wire is pointing into the board and this side is pointing out. I only care about what it is here. So you can see here the magnetic field will be going in. So is everybody convinced that this is B2, magnetic field produced by wire 2 at the location of wire 1, it's pointing in, right? Everybody with me? Look, put your thumb in the direction of current, magnetic field everywhere on this side will be in, everywhere on this side will be out. Since that wire is on that side, the magnetic field is cross, right? Okay, somebody from the fourth row, tell me now, if the current is this way and the magnetic field is cross, how will I, what direction is the force on that wire using this? Anybody from the fourth row? Use your right hand rule for the cross product L cross B2 to tell me which way should this wire feel a force due to the magnetic field produced by wire 2 at its location. Please go ahead. To the left? How many people got to the left? That's absolutely correct. So what we have is that F1 should be pointing this way. Let's do it. This time we are using the right hand rule for the cross product, right? Put your fingers in the direction of current or L and cross it in the direction of B2, which is pointing in. Do you see my thumb goes like this? So that is the direction of force F1. Hey, is this what we would have expected using Newton's third law? Yes. If that force, we already saw that if this force is pointing, say, east, then we know that this force should be west. Please.
The direction of L is pointing up and not down the wire.
Sorry?
How do you know that L is up?
Okay, the way you figure out the direction of L is always in the direction of current. So at any point, L is in the direction of current. Unfortunately, we don't call it I cross B because I itself is not a vector. So we have come up with a length vector, which at every point will be tangent to the wire itself, but in the direction of current. Very good. Is everybody with me that we have already verified at least the directions? That wire, both wires repel each other. One of them feels a force this way, the other one feels a force that way. So now let's worry about the magnitudes. Let's see the magnitude. So F1 has a magnitude which is I1, L, B2. And again, the angle between L and B2 is going to be 90 degrees. Why? Because L is in the plane of the board, B2 is perpendicular to the board, the two things are at 90 degrees. Okay, so that 90 degrees is 1. What do you think will be the magnitude of B2? Can we use Ampere's law again? Yeah, so we can go through the same exact thing. This time this is not I1, this is I2, which is carrying current down. Again, we have to find the magnetic field at a distance r away or d away if you like, and you can see that we can go through the same exact argument. This time it's not I1, it's I2, and we will get exactly the same result for the magnetic field. We'll get mu 0 I2 over 2 pi times the distance. So that means we know that B2, the magnetic field produced, this B2 has a magnitude. These crosses here have a magnitude which is mu 0 I2 divided by 2 pi d, using this. And so this is B2 is mu 0 I2 divided by 2 pi d. Look, so what is F1 over L? You can see F1 over L then, force per unit length is again mu 0 I1 I2 over 2 pi d. Isn't this what F2 over L was also? So we have verified Newton's third law. The directions in which these wires will feel the force is opposite. If one of them is east, the other one is west. And the magnitudes are the same too. So force per unit length here is mu 0 I1 I2 over 2 pi d, same as here, right? Okay, I want you to take it as a homework assignment to try to do the same exact thing for two wires carrying current in the same direction. Go through the same reasoning. This time the two wires are carrying current in the same direction. First say, okay, let me find the force on one wire due to the other one, right? And first you should find the magnetic field produced by this wire at this location. Which way is it pointing, right? The magnitudes are always going to be this. And then you can say, okay, then what should be the direction, what should be the magnitude, using the same kind of reasoning. Is that making sense, folks? Any questions about this? Please.
Why do you solve for force per unit length?
Well, because I mean, you can actually do it for force for a given length L. Remember, our assumption was that these wires are long, straight, current-varying wires which are infinitely long. Because of the fact that if the wire has only a finite length, then to some extent, if the wire is only a short wire, just like in Gauss's law, you can't really use Gauss's law to find the electric field for a finite line of charge. You have to assume that it's an infinite line of charge. So what I'm saying is that if you have a finite length wire, suppose this was the length of my wire, and will you necessarily be able to say that the magnetic field at every point has the same magnitude and direction necessarily, here or here or here or here? You can't, right? Because where you are, whether you are at the center, around this, or on one side, etc., will matter. And so what we have said is that let's not worry about that thing. We are assuming that these wires are infinite. Just like we said, oh, those lines that we were talking about on which charges were when we were trying to use the Gauss's law to find the electric field, we said, oh, let's assume these wires are infinite. So in that case, what we have done, and using this Ampere's law is a very good approximation, when R, the distance where you're finding the magnetic field, is a lot smaller than L, then in that case, you can think that the length of the wire is almost infinite. But if we have made all those assumptions, the easiest thing to do is to find the force per unit length. But no, there is absolutely nothing wrong in saying I'm going to find F1 only for a length L. So even this statement is completely correct. So this is the force on a segment of length L. You cannot find the force on infinite length wire, right? Because then it will turn out to be infinite. So you have to always choose, okay, I'm going to find, even though in my mind I'm saying, oh, this wire is almost infinite, I'm always going to be finding the force on a particular length, say for example for length L. And this statement, this formula is perfectly fine. There's nothing wrong with it. But then you can also tell me, oh, what is the force per unit length? Because in the exam, if the question is asking, find the force on a length which is 0.5 meters, then use this, right? Because you're trying to find the force on some wire, some segment of wire which is 0.5 meter long. But if you're asked, find the force per unit length, then you just need to do this. You don't need to multiply it by L. Because we can't do this calculation for an infinite wire. Do you see, if I put infinity here, then the whole thing will become infinite. So even though initially we assumed that, oh, these Ampere's law can be used for wires which are almost infinite, by almost infinite we are saying we don't really worry about these edges. These wires are so long that the length is always going to be much larger than the distance where we are trying to find the magnetic field. So for example, in these wires, if I'm trying to find the magnetic field here, or here, or here, or here, I'm okay. But if you tell me find the magnetic field, say here, do you see? I mean, the thing is, now I'm starting to see the edge of this wire. It will not be a very good approximation to say that this wire is infinite in length and I can use Ampere's law to do this. Or even if I'm trying to find the magnetic field here, if I'm trying to find it over here, am I still in trouble? Yeah, anywhere I'll be in trouble because of the fact that the length of this wire is now comparable to the place where I'm trying to find the magnetic field. So long as you're close to the wire and the distance r where you're trying to find the magnetic field is small compared to the length, it's okay to say wire is infinite in length. In that case, you can say, well, okay, so I'm going to find the force on, say, some length L, and that's what this thing is. Or you can say, well, I'm going to find the force per unit length, which is the next thing. So both of them are fine expressions, just that you cannot do it for an infinite wire. So L can never be taken to be infinite. You have to always choose a segment, and you can say, well, what is the force that this part, this little segment is feeling due to this wire? And that will be the force for length L. Or what will be the force that this little L is feeling, because we are assuming the whole wire itself is infinite. Does that make sense? Any other questions, folks? All right, then there are only two other things that we wanted to do in this chapter. One of them is finding the magnetic field due to what is called a solenoid. And solenoid may sound like a very big word, but really solenoid is nothing but just coils of wire. So for example, this. In fact, do you see that? And in fact, in MRI machine, if you have ever had an MRI scan done, people are literally shoved into a solenoid. Okay, so basically a solenoid is coil of wires in which you can pass current, and if you pass current, you can produce a very, very large magnetic field inside it. All right. Now, again, just for simplicity, because we want to be able to find the magnetic field that is produced by a solenoid, we are first of all going to assume that these wires are not this sparse. They are extremely closely wound. The second thing we are going to assume is that the solenoid itself is infinite. Okay, so this is extremely large solenoid. The ends are too far away. So compared to the radius of this, the length is so much that we'll again assume it's infinitely long. In those, if we make those approximations, we should be able to find the magnetic field that is produced by a solenoid. Suppose you need high magnetic field, it will either be a solenoid that is producing the magnetic field, and you put the thing inside here, because there will be a very high magnetic field there, as we will see in a minute, or you will use something that is called a toroid, which is like this. And what we will see today just now is that the magnetic field in this region, between these coils, can be made very large if you pass high current through it. And of course, we said that if you pass high current, yes, you will have power dissipation due to I square R, right, due to heating of the coils, because coils have resistance. You can never ignore the resistance, especially when the current is high. I square times R will become high even when R is low. So these things can be put inside, a helium chamber so that the wires become superconducting. And superconducting wires have zero resistance. Okay, so let's first talk about the physics of solenoids and toroids. But even before this, I wanted to show you another demo. We already talked about the fact that a long straight current carrying wire has magnetic field which form circles around it. Let me show you a demo. These are iron filings that actually will orient themselves in the direction of magnetic field. And let me splash it here. Right now you don't see any pattern, right? Why don't you see any pattern? Is there any magnetic field there? No, because there is no current. But as soon as I pass current, and remind me not to leave it on, because again it's going to burn the wire because the current is high, you will see what happens. So let's try to turn this thing on. Wait, where is the switch that I have to turn on? Oh, here, thank you. Okay. Okay, maybe I have put too much iron filings here, but you roughly get an idea. Do you see, this is where the wire is, by the way. Do you see that these are kind of forming closed loops here? Of course, you can't see whether it's clockwise or counterclockwise. If this current here is coming out at you, then the magnetic field will be in the counterclockwise. If the current was going into the board, then the magnetic field lines will form closed circles in the clockwise direction, right? All right, so now that you've seen for a long straight wire, let's try to do it for a solenoid. Ooh, it's already become really hot. I can barely touch that thing. It's very hot. Okay, let's try this thing and see which way is the magnetic field in this case here. Can anyone make a guess as to what we will see here? What should be the direction of magnetic field due to a solenoid? Can you make a guess? Huh? Make a guess. Huh? Straight line inside? yeah, what you will see is that inside the solenoid, the magnetic field is parallel to the axis of the cylinder that you see, right? So, and on the other hand, outside the magnetic field is extremely weak. In fact, we will see that for an infinitely long solenoid, we can pretty much ignore the magnetic field outside. So that you will see that nothing will happen to iron filings outside, and inside they will line up. Let's try and see. Okay, so right now there's no current. Let me pass a current and see what happens. Okay, do you see that inside the magnetic, these iron filings lined up along the axis of the solenoid, right? Do you see that? Outside, do you see that there's hardly any change? And that means outside the magnetic field is extremely weak. And this is exactly what will happen in real life also. And in real life applications, as I said, these solenoids can be very long, in which case we can even ignore the magnetic field outside. And that's what we are going to do today. We are going to assume that these solenoids are extremely long. Can you make a guess about what the magnetic field lines will look like for a toroid? Anybody? Go ahead, folks. Circles? Okay, basically, you are absolutely correct. In the region where these coils are, this region, what you will see is that the magnetic field lines will actually form circles here. On the other hand, in this region, the magnetic field will be 0 pretty much, and in this region, the magnetic field will be 0 pretty much. If this was a toroid which was very, very tightly wound, you will see nothing in this region and nothing in this region. Let's try and see. So here is so let's try and see what happened. Okay, do you see that pretty much here, these iron filings are actually lining up in the direction of magnetic field, but hardly anything is happening here and hardly anything is happening there. Do you see that? Okay, today what we are going to do is we are going to use Ampere's law, and we are going to try to prove that these things are really true, so that, you know, we really understand what's going on. Oops. So in order to understand this, first start with solenoid. First of all, what should be even before solenoid, I just want to ask you about one coil. So this is one, strand of coil, and let's say it's carrying current like this. I want all of you to talk to a person next to you, use your right hand thumb rule that I taught you for finding the magnetic field to tell me what should be the direction of magnetic field here, and what should be the direction of magnetic field here, and what should be the direction of magnetic field here or here, etc. So the thing is, all these questions are not about magnitude because it's about direction. Please talk to a person next to you, because I cannot do any work for you unless you have tried these things yourself. That's the only time you will really understand what I'm saying. So everybody should be working with a person next to them. All you have to do is tell me what would be the direction of the magnetic field at all those 4 points. Does that make sense? All you have is one coil, and I'm saying use your right hand rule that I taught you already for finding the magnetic field. This time it's true, it's not a long straight wire, it's a curved wire, but you should still be able to use the same right hand rule. So I'm asking at the center and at some points here. All right, folks, somebody from the last row, please. Tell me, what should be the direction of magnetic field at the center of this coil? Towards you? Okay, very good thought. Everybody agrees with him that it should be towards you? Yes, actually that is correct. The direction of magnetic field at the center of the coil should be towards you. How do we know? We can use a right hand thumb rule for magnetic field. You see, for example, let's try to find the magnetic field due to this little segment here of wire. I put my thumb in the direction of current. Magnetic field lines will form closed circles around the wire, right? So do you see that if I put my thumb like this, on this side the magnetic field is crosses going into the board, and then here it's coming out, right? What about over here? Anybody? Huh? Very good. It should be going in here. What about here? Again, going in here, going in here. How do we figure it out? Put your thumb in the direction of current. You can see magnetic field line is going in here. It's true. Outside is a little bit, you might say, oh, what about due to this part of the wire? It's true that this part, the magnetic field here is going in, and on everything here it's coming out, right? But the point is that if suppose, you are looking at some point like this over here, then the magnetic field due to this current here is going to be stronger here than the magnetic field due to, say, some segments here. But I want you to focus on inside. Notice something very interesting about inside. Does all of the current in every little segment of this loop produce magnetic field in the same direction at the center? Yes. So whether I put my thumb like this in the direction of current here, look, magnetic field is into the board due to this segment here, and due to the same segment, it's out here. Here again, in and out, in and out. So do you see that all the segments of the wire are producing current that is coming, magnetic field that is coming at you inside, right? Okay, now think about a solenoid. Solenoid is nothing but lots of these loops wound very closely together. So a solenoid would be, this would be the axis of the solenoid. So one perspective of solenoid is like this. And assume these things are very, very closely wound. And if I told you that the current in one of the windings, so for example, look at this, this has lots of windings here, lots of windings of wire, right? If I told you that the current is flowing this way, can you again use the same exact right hand rule that you used just now, and you can say, oh, if the current is like this, magnetic field should be like this, right? Put your thumb in the direction of current, the magnetic field, right? So does everybody see that outside the magnetic field could be in one direction, and inside it's definitely going in? Of course it's a little bit more complicated if you're looking at points over here and over here, because you have to take the vector sum of all of these magnetic fields due to all these little elements. But let's just focus at the center here. Does everybody see that the magnetic field is really going to be pointing in this way? Now if this solenoid is long enough, all of the magnetic field inside is pointing that way. So basically, and that's what you were seeing, what you saw is that the magnetic field was along the axis of the solenoid. It was this way or this way. Now whether it will be that way along the axis or this way will depend upon whether the current is flowing this way in these wires or this way, right? But does everybody see that what I will do, what you should do is put your thumb in the direction of current. Let's say the current is flowing this way. Put your thumb in the direction of current, and you can see inside the magnetic field will be going that way, right? If the current was coming towards me like this, then put your thumb in the direction of current, and you can see the magnetic field is inside is going that way, right? Okay, so everybody is convinced that the direction of magnetic field inside the solenoid is going to be along the axis one way or the other depending upon the direction of current. Now I am going to consider an infinitely long solenoid because I want to be able to use Ampere's law now to find the magnitude of magnetic field, not the direction. Direction we have already figured out, nailed it. So let's do the magnitude. And this is like infinitely long. Okay. And by infinitely long, again, in your mind what you're thinking is that the radius of this thing is a lot smaller than the distances. So basically what we are saying, infinitely long means that this length is very large compared to this radius, so that we don't worry about the edges. Let's not worry about edges. Okay, if that is the case, everybody agrees already with me that magnetic field is either going to be pointing this way or the other way, depending upon, because this solenoid is obviously connected to some battery, right, in order to pass current through it. So you can see if the battery is connected this way, the current will be flowing this way, right? What happens if I connect the battery the other way? If I could connect the battery like this, in which case the current will be that way. So I'm not going to worry about the fact that you can connect the battery two ways. In each of these two cases, the magnetic field inside will be either that way or the other way, right? But it will definitely be along the axis. Is everybody convinced of that? So these are the magnetic field lines, B. Whether it's pointing to the right or to the left will be determined by the direction in which the current is flowing. Let's say that the magnetic field is pointing like this because of the fact that the current is going this way. Okay? All right, don't worry about, I don't want you to get confused about this. So the important thing is I have chosen a direction such that the magnetic field is going that way because of the current. I want to know what is B magnitude. Here is the thing, before we do B magnitude, one thing you have to remember is magnetic field lines always form closed loops. If they form closed loops, these magnetic field lines are not going to stop there. They are always going to go around and somewhere they are going to go and loop. Here it's not going to stop here, it's going to go around and it's going to loop. This one is not going to stop here, it is going to go around and loop, right? On the other hand, think about this. The space inside this solenoid is very restricted and all of this field lines inside the solenoid is pointing in the same direction, and all these field lines need to turn around somehow and get back and loop back to this point. Do you see that these field lines have the rest of the universe to turn around? So while inside all of the magnetic field that is produced by these wires in these windings are all pointing in the same exact direction, outside you have so much space to have these things turn around. So outside these field lines are going to be so far away from each other that density of field line, which is a measure of how strong the magnetic field is going to be so small that you can ignore the magnetic field outside. So outside the magnetic field is almost zero. You can forget about the fact that these field lines are even there outside this solenoid. It's almost zero because these wires will turn it, loop around, all the way, very, very far away from this thing as well. And that is why you were seeing, when I showed you the picture, you saw nothing happen to the iron filings here because the field is extremely weak. Okay, so we are ignoring the field outside this solenoid. Once we ignore the field outside, now we have to use, in order to use Ampere's law, we have to say, hey, what will be a good loop to choose here? Because we have to choose we have to take a thread and we have to loop it around like this, such that we are able to exploit the symmetry of this problem to find the magnetic field magnitude. This is what we are after. Does anybody have a thought on what kind of loop we can choose, Amperian loop, in order to use Ampere's law? Any thoughts, folks? So the question is this. We want to use this integral b dl cosine theta is equal to mu 0 times I enclosed. We want to know, what kind of loop should we choose? We have to choose a closed loop, Amperian loop. Go ahead, please. Okay, this is this is a one-dimensional thing. So either you tell me circle or you tell me rectangle or something like that, because cylinder sounds like a three-dimensional structure, right? That was the case for Gauss's law. You chose sphere, you chose cylinders and other things. But here, the thing is, what do you mean? Do you mean like a rectangle or? Yeah, it turns out that the best thing to do here, if suppose you are telling me, find the magnetic field here. What is the magnitude of magnetic field at some point here? Obviously my loop needs to be such, the closed loop needs to be such that it includes that point. A good choice of loop, you know, I'll take a thread and I'll put it around the thing, will be, say, choosing something like this, say a rectangle like this. And I'll tell you in a minute why a rectangle like this would be a good choice. All right, and I will decide to choose my DL, because remember, you can choose your DL, which is the length vector, to be either clockwise, the counterclockwise, or clockwise. Let's choose, just for simplicity, let's choose it in the direction of magnetic field. So we will go like this over there. So this is the direction of DL. Okay, so little DLs will be like this. Little DL here is like this, little DL here is like this, etc. Okay, now here is the thing. If we are saying the magnetic field here is 0. Remember we said magnetic field here is 0. Why? Because I just proved to you that all these field lines outside have the rest of the universe to go around, so the field is extremely weak. In fact, you saw that it was almost 0. So we know that B outside is 0 here, B outside here is 0. So B, do you see that at all these locations the B is pretty much 0? Okay, so we don't even have to worry about this part of the loop. Let's call it A, B, C, D. And this integral over this closed loop can be broken up into 4 parts: AB plus BC plus CD plus DA. These 4 integral B dl cosine theta is equal to mu 0 times I enclosed. So the thing is, what would be the what is this? Integral from A to B, or B to C, C to D, or D to A. Let's do it one by one. So here from C to D, does everybody see that B is 0? If B is 0, then wouldn't integral B dl cosine theta be 0 if B is 0 everywhere? So from C to D, I don't have to bother with this integral at all because this is 0, I know. What about these 2 parts from, you know, D to A or B to C? Tell me. First of all, this part I don't have to bother. This part I don't have to bother. The magnetic field is 0. What about here, for example? Think about here. DL is like this, right? DL is like this, right? Which way is the magnetic field? Is magnetic field that way? Do you see what is the angle between the magnetic field and DL? It's 90 degrees. So does everybody see that for this segment here and this segment here, the angle between the magnetic field, which is along the axial direction, and DL, which is pointing that way, is 90 degree, and cosine of 90 is 0. If cosine of 90 is 0, then for those segments there is not going to be any contribution to the flux. So in other words, this will give me a 0, sorry, not flux, but there won't be any contribution to B dl cosine theta. Does that make sense? So the only contribution that you get will be from this part AB. Do you see that in this part AB, the direction of magnetic field is that way, and that's also the direction of DL. So for that part, this cosine theta is cosine 0, and cosine 0 is 1. So basically what we are saying is we are left with integral from A to B, B dl times cosine of 0 degrees, and that should be equal to mu 0 times I enclosed. Cosine 0 is 1. Okay, now would you say that the way we have chosen our loop, that the magnetic field magnitude is constant everywhere here? Isn't it? So if the magnetic field magnitude is constant, I can pull this B out, and this becomes B integral A to B dl, which is equal to mu 0 times I enclosed. What is integral from A to B dl? What is this? That's just the perimeter of this part, or just the length rather, the length of this part, right? Let's say that I chose a loop which has a length L. I can choose my Amperian loop to have any length. You will see length should drop out from the answer. The answer, the last answer should not have any length in it. So here I'm choosing a loop of length L. So then this just becomes B times L times is equal to mu 0 times I enclosed. And that means that the magnitude of magnetic field should be mu 0 I enclosed divided by the length. Now I claim that L shouldn't matter. Why shouldn't it matter? Because the thing is, how can you choose how can it matter what is the length of the Amperian loop I choose? You could choose a different length. Now here is the thing, what is I enclosed? We still need to find what is I enclosed. In order to find I enclosed, here is the thing, let me define a few things. I'm going to define something called number of turns per unit length. That will be little n. Let's say I is the current in one turn. Who wants to tell me what is the current enclosed in terms of those two things? Go ahead. Ni. Because if n is the number of turns per meter and L is the length, maybe it's 0.5 meter, maybe it's 0.75 meter, whatever it is, it's the length of this Amperian loop that I chose in this direction. You can see that the current enclosed should be the current in one turn times the number of turns per meter. Sorry, there is one more thing. L. So the thing is, so the total current enclosed should be equal to N times L times I. Is everybody with me? Because N times L will tell me how many turns of wire there are here in this region, and times the current in one turn. Okay, great. So then I can write here, let me use this here, and I can see that B turns out to be mu 0 times N L I divided by L. L and L get cancelled. The magnitude of magnetic field is mu 0 N I. This is the final answer. So you can see that the magnetic field inside a solenoid only depends upon the current and the number of turns per unit length. That's it. Does it depend upon the radius? No, it does not depend upon the radius of this thing. But remember, the reason radius doesn't matter is because we are assuming that this thing is way large compared to the radius. If your solenoid is not very large, all these approximations that we have made will not work. You can't then say the magnetic field is 0 outside, etc. So the radius does not matter for an infinitely long solenoid. Please.
Is the current in one turn just the current that's like passing through the wire?
Right.
Okay.
Yeah, exactly. Absolutely. Any questions about this? Anybody? All right, wonderful. So now that you understand something about solenoid, let's extend this result to a toroid. Toroid is this kind of a thing. This thing. And you already saw that for a toroid, the magnetic field inside is like this, right? Along the axis of the toroid here, like along these, like this. And outside, the magnetic field was very weak here. We can almost assume it's 0. Here, it's almost 0, right? But let's try to actually see what turns out to be the magnitude of magnetic field in different regions for the toroid, all right? So, and it's going to be very easy. Again, we are going to use Ampere's law to do this. Okay, so we have something like this, which looks like something of this sort. Okay, so do you see that there are 3 regions here? What are the 3 regions? One region, let's call this thing, this inner radius, something, what do you want to call it? A. Let's call this outer radius, let's say B. And so there are 3 cases here. I have to find B magnitude for some r less than A, B for r between greater than A but less than B, and B for R greater than B. Let's try to do all these three cases, all right? It's going to be easy. Let's try it now. So basically we want to again use Ampere's law, obviously, because remember the other thing that we learned, Biot-Savart law, we said that that will require us to do integrals, complicated integrals. Biot-Savart law was very much like doing Coulomb's law for electricity. So that was very complicated. So we said, no, we will use only those cases where there is high level of symmetry and we are able to use Ampere's law. So let's try Ampere's law in this case, case 1. Case 1 is B for R less than A. Here is the thing. If suppose you were not convinced that the magnetic field in this region is 0, like what this thing showed almost, the picture that I showed you of the iron filing, suppose you were not convinced that the magnetic field, let's say we choose some distance here, R, all right, which is less than A, and you are saying, tell me the magnitude of magnetic field here. Suppose this is what you're asking. Okay, so you're not convinced that it's 0. I'm going to prove to you that it's 0. I will prove it to you. How do we prove it? We are going to make use of Ampere's law, which says integral B magnitude dl magnitude times cosine of the angle between the two should be mu 0 times I enclosed. Suppose you were not convinced the magnetic field was 0 here, then I will say, okay, let's choose a good Amperian loop that we can find. Is a good Amperian loop here this that passes through that point that is a circle? Yeah, that's a really good Amperian loop, because from the symmetry of the situation, will you be able to vouch, if you were not convinced that the magnetic field was 0 at every point, will you at least vouch that the magnitude of magnetic field due to all this current carrying coil should be the same at every point? From the symmetry of the situation, should it? Yes. So then you will say, oh, then I should be able to pull this out. Also, you can easily convince yourself that the direction of magnetic field can only be either clockwise or counterclockwise. It cannot be any random direction, because then you will say, why not this other direction? Do you see that? So if that's the case, then the direction of dl and B will be the same, and this is cosine 0 degrees. And this should be mu times I enclosed. Notice that what will be integral dl here for this Amperian loop? Is it just the perimeter 2 pi r? Isn't it? So what we have here then is B times 2 pi r is equal to mu 0, this is just 1 cosine 0, mu 0 times I enclosed, and what I get is that B is equal to mu 0 I enclosed divided by 2 pi r. The only thing that we need to do, so this is the magnitude of magnetic field at a distance r away where this distance is less than A. Now the question that I have for you is, how much is the current that is enclosed here? Think about it. Look, remember we said how to find the current enclosed. We said if you choose the loop in a certain direction, suppose I choose my dl to be like this, you know, then we said you put your fingers in the direction of the loop, the dls, and anything that points towards you, we'll choose it as positive current. Anything that points away from you, we'll choose as negative current. Do you see here, first of all, that there's no current enclosed at all here? Is everybody seeing there's no current enclosed in this region? So the current enclosed is 0. So case 1 is very easy. Oops. Okay, so you can see that since I enclosed is equal to 0, what do we get? As soon as I put I enclosed equal to 0, I get P is equal to 0. So I'm hoping at this point I have been able to convince you that there is no magnetic field in this region here. No matter what R you tell me to choose, the magnetic field is 0. Okay, what about case 3? Let's do case 3 because that's also an easy one. So for case 3, I have some point over here. at a distance r away, and you are saying find the magnetic field here. Should I again choose an Amperian loop to be passing through this, which is a circle? Shouldn't I? Yes. So I can choose my Amperian loop to be passing through this loop like this, which is a circle. Again, from the symmetry of the situation, if you were not convinced that the magnetic field here is 0 or here is 0, 0, 0, will you at least be convinced that the magnetic field produced by all this current in this toroid is the same at every point here? You will be, right? So you will again be able to pull the magnetic field out. All this stuff still passes through. We are still here, right? The only thing is, how much is the current enclosed now? Can you make a guess? So if I had some point here and you're asking what is the magnetic field, I have chosen my Amperian loop like this to be a circle which is symmetric with respect to this. Now we have already figured out the magnetic field magnitude is mu 0 I enclosed over 2 pi r. The question is, what is the current enclosed in this loop? I claim it is 0. Why is it 0? Because if you look at these windings, every time the current is going in towards me here, it's coming out towards you there. Do you see every winding is like this? Right? So if suppose the current was flowing such that everywhere here the current is coming towards me, everywhere here the current is coming towards you. Do you know what I'm saying? It's like this. So the net current enclosed is 0. Does that make sense? Okay, so basically what we are saying is, again, for case 3, I enclosed is equal to 0 because current coming out at you and current coming away from you, they cancel each other out because there are as many windings that go towards you as away from you. All right, now let's try to do case 2. So case 2 is this one. Case 2 is the case where I am looking at some point here between A and B. So this time I'm somewhere over here. You are asking me what is the magnitude of magnetic field over here. This time I'm going to choose my Amperian loop like this. Again, passing through that point. Again, from the symmetry of the situation, can you tell me that the magnitude of magnetic field definitely is the same everywhere? You can, right? So again, all of the arguments that we gave over here still holds, and we are here. Isn't it? Don't you think that the whole thing again flows through? The only thing now is, this is R is greater than A, it's less than B. This time again we are here. B turns out to be equal to mu 0 times I enclosed divided by 2 pi r. Now the question is, in this particular case, let's say that I is again the current in each turn of the toroid, and let's say n is the total number of turns. Then can you tell me what is the current enclosed? This time we are talking about some point here, and you are asking me what is the magnetic field there inside this, and we are taking a loop like this, right? What would be, do you see that this time we are either taking all the things that are going towards you or away from you, right? Because this is not enclosing, it's only enclosing these currents which are either going towards you or away from you depending upon whether the current is flowing this way or that way, but not these ones, not the outside ones. So there is a net current enclosed in this case. Is everybody seeing that there is a net current enclosed here? Okay, if there is a net current enclosed, what should it be? Tell me. Should it be just I times n? Right? Shouldn't it? Divided by 2 pi r. And that is the final answer. You can see that the magnetic field due to a toroid is again proportional to the current. It is proportional to the total number of turns, and it's inversely proportional to the distance r from the center, so long as you stay in this region. R could change, right? R could be anywhere, it could be right here, or it could be here, or it could be here, or it could be here, etc. So long as you're inside this region here, right? Is there any questions, folks? So notice that unlike the solenoid, where the magnetic field does not depend upon the radius. Here, in the case of toroid, the magnetic field does depend upon the distance r from the center, so long as you're trying to find the magnetic field in this region here, between the coils. Here the magnetic field is 0, here the magnetic field is 0, this is case 1, this is case 3, and in case 2, we are saying, yes, if you are looking at magnetic field at different distances r, things will depend upon r. In a solenoid, it didn't. But then we assume that the solenoid was infinite in extent. Any questions about this, folks? Anybody? Okay, then we are done with magnetostatics. So, remember what we, let's go slowly. So the thing is, what did we talk about so far? We started this course with electrostatics, right? Means charges at rest, and we were talking about, what is the force between the charges, what is the electric field produced by those charges, etc., etc. What is the potential energy stored in these charges, etc., etc. Those were the things that we've talked about, assuming charges were at rest wherever they were. So we were always considering equilibrium situation. Then we moved on to moving charges and currents. We talked about Kirchhoff's rules, we talked about how to find the current in different parts of the loop, how to figure out what was the current density, how to figure out what would be the resistance, what would be the potential difference, given certain things. If you are given the voltage of the battery, you can find other things, etc. Okay, that was moving charges. Then we moved on to talking about magnetostatics. By magnetostatics, I mean we are talking about cases where the magnetic field is constant. So if the magnetic field is produced by, say, some wire, some current I in the wire, this is it. The magnetic field is a constant in this case. So this is what we'll call, say, magnetostatics. That means magnetic field which is not changing. Now we are going to move on and talk about cases where the magnetic flux, I'll define it in a second, but the magnetic field, let's say, is changing with time, or maybe magnetic field is not changing, something else is changing, so that the total number of magnetic field lines through some loop is changing with time. We will define something called magnetic flux, and what you will see, lo and behold, what you will see is that there is, after all, a connection between electricity and magnetism. If you cut the magnet in two parts, it's not like you get north pole here and south pole here. What you get is north and south, right? When you do that with bar magnet, because magnetism is a totally different thing in the sense it's produced by the spin of the electron, or it's produced by moving charges when you're talking about current carrying wires. But it doesn't, magnetism and electricity are not the same. From now on in this course, now that you understand electrostatics, currents, magnetostatics, we are going to move on to showing that even though magnetism and electricity are totally different things, they are intimately related to each other. So the next few chapters are all about how to find the connection between electricity and magnetism. We will see that if there is a change in the magnetic field, for example, through a loop, even without a battery, you can produce a current there. Isn't that weird? So look at this. This is very, very bizarre. So I'm going to show you something that is really cool. Here is, now where in the world is this switch here? Anybody knows this? Okay, here. Okay, great. So look, here is an ammeter. Okay, this is an ammeter. What is it reading? 0, right? Why? Because this ammeter is trying to read the current in this coil. This coil is not connected to any battery. Do you see any battery? No. All it is connected to is that ammeter that will measure a current if there's a current through it. It's measuring nothing. Do you know what will happen if I bring a magnet close to it? Watch. Did you see what happened when I brought the magnet close to it? Now I'm holding the magnet fixed. Do you see any current? No. The ammeter reading has gone to 0. That means there is no current. Watch what happens when I take this magnet away from the coil. Again, at the moment I was taking away, did you see that there was a current? All right, now, earlier I was taking the north pole close to it, or I was taking the north pole away from it. Can you make a guess what will happen if I take the south pole close to it? The direction in which the current will flow, in other words, the direction in which the ammeter will deflect, will be opposite. So watch, I'm bringing the south pole close. Did you see the current was that way? And I'll also show you what happens when the north pole is brought. Do you see it was different? The thing is, this is a very, very bizarre phenomena. First of all, if I hold the magnet stationary, now I'm holding it stationary, yeah, magnetic field lines are going through this coil, but nothing happens, there's no current produced in this coil if I hold this magnet stationary. The only time there's current produced in this coil is when I move the magnet away or if I bring the magnet close. Or the other thing that I could do is move the coil itself. Watch what happens when I move the coil. So in other words, what I'm changing is the angle that the area vector is making with the magnetic field. And again, if I hold it fixed, nothing. So there is something very, very bizarre about this, but all of this phenomena can very easily be understood, and this phenomena will be the first instance in which we will try to see the connection between electricity and magnetism. Because this is showing that somehow when I change the magnetic field that is passing through that loop, this loop here, in which there is no current, somehow miraculously there is some current induced there. Some current is produced there. This phenomena is called Faraday's, this phenomena by which the current is induced is called Faraday's law of electromagnetic induction. And let's talk about it because it's a very interesting phenomena. What it says is that whenever there is a change in the magnetic flux through a loop, there is a change in the magnetic flux. Through a loop. A current is induced. And an EMF is induced. And this EMF that is induced is called induced EMF. The current that is induced is called induced current. Do you know how the two things should be related to each other? If I told you the resistance of the coil, if I told you how much is the total resistance of the coil, and I said, oh, the EMF that is induced, let's call it E induced. Actually, let me write it as V induced so that you don't get confused. This is the EMF that is induced, and the current that is induced, let's call it I induced. Suppose the resistance of the coil is R. Who wants to tell me what should be the relation between the amount of current that is induced and the amount of EMF that is induced? Go ahead, folks. Anybody? What should be the relation between V induced and I induced? Go ahead, please.
V induced is R induced.
Excellent. This is Ohm's law. V is equal to IR. So we know, if we know the resistance of the coil and if we know the current induced, we can find the voltage induced or EMF induced, and vice versa. If we know the EMF induced, we can find the current induced, right? Okay, according to Faraday's law, the induced EMF is related to changes in magnetic flux. Now, what do you think is magnetic flux? Just by analogy with electric flux, can anybody say what should be magnetic flux definition? Let me remind you what is electric flux. Electric flux was this. Actually, you don't even have to have it over a closed loop. It was just integral E dot dA, which was integral of magnitude of electric field, magnitude of the area vector, times cosine of the angle between the electric field and area vector. Can anybody from the second row, using this analogy, tell me what should be the definition of magnetic flux? You know, because this is talking about magnetic flux. It says whenever there is a change in the magnetic flux, there is an EMF induced, there is a current induced. What should be the definition of magnetic flux? Go ahead, somebody from here, second row. Can you make a guess? I can bet you it has to come out right. Your guess will definitely come out right. Can anybody make a guess? Go ahead, please. Very good. The definition of magnetic flux, instead of electric field, you use magnetic field, right? So this will be B dot dA, which should be equal to integral of the magnitude of magnetic field times the infinitesimal area vector times cosine of the angle between the magnetic field and area vector. So notice that magnetic flux depends upon how many things? 3 things. It depends upon the magnetic field, it depends upon the area vector, and it depends upon cosine of the angle between the two. Doesn't it? So if I pull, suppose if B is constant, magnitude of B is constant, and let's say cosine theta is constant, because the surface is flat, then can I pull B and cosine theta out? I can, right? So the thing is, by the way, let's give it a symbol also. We'll call magnetic flux, let's give it a name. We'll call it phi of B. Just like electric flux, remember we used to call it phi of E. Here we are going to call it phi of B. Just a name, you know, shorter name. So if B and cosine theta are constant, we can say that the magnetic flux should be B pulled out, cosine theta pulled out, integral dA. What is integral dA? Magnitude of integral dA? Is that the total surface area? Right? All you're doing is integral means adding up, summing. You're summing all the little areas, dA, 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 dA. When you add it up, you get the total surface area. So what you have is this. Phi of B is equal to magnitude of B, magnitude of total area times cosine theta. This is the magnetic flux. So is everybody convinced that there are 3 things that magnetic flux depends upon? The magnetic field, the area vector, and the angle between the two. You know, when I'm bringing this thing close to this thing, do you see I'm changing the magnetic field lines? Magnetic flux is really a measure of the total number of magnetic field lines that are going through an area. Just like electric flux is a measure of the total number of electric field lines that are going through an area. Do you see that if I bring this thing like this, I'm increasing the magnetic flux through it. If I bring it away, I'm decreasing the magnetic flux through it, right? If I hold it fixed, I'm not changing anything. If I don't change it, the important word here, I cannot emphasize, the important thing here is this change. There needs to be a change in the magnetic flux passing through a loop in order for there to be a current induced and an EMF induced. So if I hold this fixed, are you seeing anything here? Nothing, right? Because is the flux fixed right now? There is no change in the flux. If I pull it out, if I push it in, if I pull it out or push it in, yes, I do see a change. Because during those times that I'm making the change, the flux is changing. And there is a change in the magnetic flux, and hence there will be an induced EMF and induced current. If I change this angle between the area vector and magnetic field, do you see again we'll see the change. If I had taken a different area, suppose this was a coil that I could collapse or expand, should I have seen that during the time I'm making the change in the area? Should I have seen an induced current and induced voltage? Yes, because there are 3 ways to change the magnetic flux: by changing the magnetic field, by changing the area, and by changing the angle between the two. Now the statement, if I want to put this Faraday's law in mathematical form, here is how I would do it. So Faraday's law in mathematical form says this. It says that the induced EMF should be equal to minus n times d phi over dt. What is n? N is the total number of turns of the coil. What is phi of B? That's the magnetic flux. So if B is constant and the angle theta is constant, basically what we have here, if the magnitude of magnetic field and theta are constants, then basically what this thing says is that V induced is equal to minus n d over dt of magnitude of B times magnitude of A times cosine theta. D over dt is the rate of change of flux with time. Everybody is familiar with derivatives? Derivative with respect to time is the rate of change of flux with time here. So you can see that there are three ways the flux can change. Either you're changing the magnetic field, you're changing the area vector, or you're changing the angle between the two. Right? Theta? Does that make sense? Okay. In many problems, you might be given a problem in which you are given, for example, the magnetic field at this time is this, the magnetic field at this time is this, the area stays the same, the angle stays the same, what is the induced voltage? If that is a problem that you're given, then you will just do it like this. So suppose you have a problem in an example. Suppose you are given that B magnitude was 0 at time t equal to 0 and B magnitude is equal to say 0.5 Tesla at, say this is T1 at T2 is equal to 5 seconds. And suppose you are told that n, which is the number of turns of coils, is 1,000, and suppose you are told that the area vector has a magnitude of say 2 meters square, and you are told that theta is fixed and it's 30 degrees, and the question that you are asked is what is the magnitude of V induced? How do you think we are going to do this? You know, you can change the derivative into differences, deltas. First of all, since we are asked for the magnitude of V induced, we can do it like this. So that V induced magnitude, don't worry about the minus sign. I'm going to talk to you about minus sign next time. All right? The meaning of the minus sign is given by what is called Lenz's law, which we'll talk about next time. Let's just try to do this problem today. We have this d over dt. We have, what we can do is we can call it delta phi over delta t. We don't care about the sign times n. So all I have done is I've changed the derivative into difference, delta phi over delta t. So what is this? That means that V induced is equal to n times phi b final minus phi b initial divided by T2 minus T1. What is phi b final and phi b initial? Can you guys find it out yourself? It will be B times A times cosine theta. And notice initially it will be this B times this area times this cosine theta. Finally it will be this B, this area times this theta. Does that make sense? So plug everything in and you will be able to find what is the induced EMF in volts. All right. Have a great day, folks. I'll see you guys next time.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.